In this example, we will look at the potential that is experienced by a point charge as it approaches a different charged object. For example, we will consider a charged sphere with radius capital R and charge Q1, which is approached by a point charge Q2 at a certain distance. Question is, what is the potential experienced by Q2 as a result of the proximity of Q1? For this, we will use the expression for delta V, which we have seen in the lectures. Delta V equals minus the integral of E times dr, where E is the electric field at the location of the point charge. Now we know that the force acting on charge Q2 is the Coulomb force, F2, which can also be written as Q2 times E. So we can rewrite this expression over here as minus the integral of F2 divided by Q2 times dr. Now in this situation, F2 and dr are pointing in the same direction, they are both horizontal. So this vector product we can just replace by a scalar product. So just F2 times dr to keep it simple. And the magnitude of F2, which is the Lorentz force, can be written as follows. So F2 equals K Q1 Q2 divided by R squared. So I can rewrite this integral as minus the integral K Q1 Q2 divided by R squared Q2 dr. Now since there is a Q2 both in the numerator and the denominator, I can cancel those, and I can also take some constants in front of the integral. So I arrive at minus K Q1 integral 1 over R squared dr. Now this is a potential difference, so we should consider the fact that there are two different locations here that we're comparing to each other. Let's call those positions RA and RB. And for now, we'll just write it as such. We'll define those locations in a moment exactly. So now with these boundaries, we can actually compute the integral. So this can be written as minus K Q1 times minus 1 over R from R equals RA to RB. Now the way these RA and RB are defined is that RB is the location of the point charge, and RA is the reference, which we always choose as infinity. So RA is out there in infinity, which means that if I write this out as follows, K times Q1 1 over RB minus 1 over RA, that this second term over here will always be 0, because we always define the potential with respect to infinity. So in other words, the potential felt by a charged particle at a location RB will be simply K times Q1 divided by RB. Now if I would calculate this for different locations RB along this line, I would get a function that looks like this. So this is delta V, this is RB, and I see that it goes down like 1 over RB. And that continues up to the point where we reach the edge of the sphere. If the sphere would be a point charge itself, it would continue into an asymptote, and it also continues onto an asymptote here on the right. This is the potential, and importantly, the potential only depends on the magnitude of Q1, so the magnitude of the charge of the sphere, and not of the point charge approaching. So this sphere has a potential field of its own, which is independent on whatever other charge is approaching. But now we're interested not just in the potential, but also in the potential energy that is experienced by this charged particle Q. So we know that the potential energy, delta U, will be the charge, Q2, times the potential. Now, if Q2 is positive, then that will be a very similar graph. So here I plot again R2, the location of, apologies, this should be RB, the location of the point charge. Here I put the potential energy, and I get a very similar function that looks like this. This is if the charge Q2 is positive. But now imagine that we make this point charge negative. For example, an electron that approaches the nucleus of an atom, which is itself positively charged. So now we have the situation Q2 is negative. Then we see that we have to multiply this potential, which is always positive, by a negative number, and I get a curve that looks like this. So now we see that if a negative charge approaches the positively charged sphere, it experiences a potential energy which goes down, and therefore it is attracted towards the nucleus. Whereas when a positive charge approaches it, it experiences a potential energy that goes up, and therefore it is repelled by the sphere. And that concludes this example.